Hello physics students, and welcome to this video about simple harmonic motion. In this video we're going to take a look at periodic motion, simple harmonic motion, Hooke's law, the conservation of mechanical energy, and the simple pendulum. Let's start by looking at periodic motion. What is periodic motion? It's basically the repeated motion, the back and forth over the same path of an object. All of these different pictures represent periodic back and forth repeated motion. One very simple example of periodic motion is when we have a mass attached to a spring, and we'll assume a frictionless surface, and let's say that at rest or at equilibrium we have the mass attached to the spring. If we either pull that mass or compress that mass and then release it, the spring will cause that mass to vibrate back and forth around that unstretched position. So let's start by considering this equilibrium or unstretched position. We'll say x equals 0 at this point. Now let's say we stretch that spring away from the equilibrium position such that we have some distance x now away from that unstretched position. The spring is exerting a force on the mass back toward the equilibrium position. As that mass is being moved back toward the equilibrium position, this force will decrease until it reaches 0 right at this equilibrium position. The same thing will happen with the mass's acceleration. It will continue to decrease until it's 0 at this equilibrium position. The velocity is a little bit different, on the other hand. The velocity will increase until it reaches this equilibrium position. And when the mass reaches this equilibrium position, its velocity here will be at a maximum, as opposed to 0 acceleration, 0 force. Although it reaches its maximum right here, and although we have no net force acting on it at that point, the mass's momentum itself will cause it to overshoot the equilibrium position and compress the spring until we get to this position. So as the mass moves beyond this equilibrium position, the spring force or the elastic force here and the acceleration are going to begin to increase. But the direction of the force and the acceleration is toward equilibrium. So it's opposite the direction of the mass's motion, which is away from equilibrium. So the mass begins to slow down. So once the spring's compression is equal to the distance that the spring was originally stretched away from equilibrium, here, negative x as opposed to x, then the mass is at its maximum displacement, and the spring force and the acceleration of that mass reach a maximum. The velocity, on the other hand, of the mass becomes 0. The spring force acting to the right then causes the mass to change direction. Mass begins moving back toward this equilibrium state position, and you start the whole process all over again. So in review, our elastic force and our acceleration are at their maximum here and here. The spring force and the acceleration are at 0 right here. We have, on the other hand, velocity being 0 in this position and this position, but maximum velocity is achieved as the mass travels through the equilibrium position. So in a frictionless ideal world, this mass spring system would oscillate indefinitely. However, due to friction in the real world, the motion of this vibrating mass eventually comes to a stop and comes to a rest. That effect is called damping, and in most cases that effect of damping is very minimal over a very short period of time. So this system gives us a nice approximation for the motion of a physical mass spring system. Now in this example, the spring force, that elastic spring force, is pushing or pulling the mass back toward the original equilibrium position. Sometimes that force is called a restoring force. And in our system, this restoring force is proportional to the displacement of the mass. Greater restoring force causes greater displacement of that mass, or lower restoring force causes less displacement. Anytime we have a periodic motion in which a restoring force is proportional to the displacement from equilibrium, we call that simple harmonic motion. That's the definition for simple harmonic motion. So in 1678, a man named Robert Hooke found a nice, tidy little mathematical relationship for small displacements from equilibrium in our mass spring system, and that is called Hooke's law. It is that the spring force is equal to the negative product of the spring constant times the displacement. The negative sign in the equation tells us the direction of the spring force is always opposite the direction of the mass's displacement. Or in other words, the spring force is that restoring force that tends to move the object back to its equilibrium position. The value of the spring constant K, we've worked with this before, measures the spring's stiffness. A greater value of K means a stiffer spring. It's always positive. Its SI units are newtons per meter, meaning obviously that our displacement will be in meters for this equation, and the force will be in newtons. So let's do a little example. Let's say we have a spring with a spring constant of 1,962 newtons per meter, and here we have it. It loses its elasticity if it's stretched more than 50.0 centimeters. This kind of looks like more than 50 centimeters. What's the mass of the heaviest object the spring can support without being damaged? So if we write down what we know the spring constant, we know x, the displacement here, convert that to meters. What is the mass of the heaviest object that this can support? We know that our formula for Hooke's law is this, and we know we can find the force. How are we going to find the mass? Well, we also know that force equals mg, so we know gravity, the acceleration due to gravity, and so we can therefore determine the mass using these two equations. So we get our force equal to 981.0 newtons in the opposite direction of the displacement. We can then use that information to determine the mass using this equation. Now remember that a newton is a kilogram meter per second squared, so when our units all cancel out, we're left with our mass in kilograms. And we can write it like this, since we can have 3 sig figs, and that is the maximum mass that our object can have without damaging this spring. So a stretched or compressed spring has elastic potential energy. How is mechanical energy conserved in an ideal mass spring system? Well, let's just take a look. This isn't a mass and a spring, but this is a slingshot. Very similar system because elastic potential energy is stored in this slingshot when it is being pulled back. If an object is placed in here and the user pulls this back and stretches these bands are storing that elastic potential energy. While the user is holding this band back here and storing that elastic potential energy, kinetic energy of the system is 0. So the mechanical energy of this system at that point is solely elastic potential energy. But when the person releases that and hurls whatever object is in there through the air, the elastic potential energy from this system, from these bands, is converted into kinetic energy of the object hurling through the air. At the very moment this object it leaves this slingshot and starts to hurl through the air, it gains nearly all of that elastic potential energy. A little bit of that elastic potential energy is converted into kinetic energy of the slingshot itself and these bands. So once that object has been released from this slingshot, we know that because of conservation of mechanical energy, the kinetic energy of the object and of this slingshot itself all together is going to be equal to whatever that elastic potential energy was that was originally stored in that slingshot. So as we've seen, the periodic motion of a mass spring system is one example of simple harmonic motion. Let's look at another example of simple harmonic motion, the simple pendulum. In this picture here, the motion of these acrobats is forming a physical pendulum. We're going to simplify this motion and look at a simple pendulum. A simple pendulum consists here of a mass, which is called a bob, and it's attached to a string that's fixed. And when we work with simple pendulums, we assume that the mass of this bob is concentrated at a point and that the mass of the string is negligible. We also disregard effects of friction and air resistance. For a real-life physical pendulum, like this one, we would have to consider the mass, the distribution of the mass, friction and air resistance as well. But we're going to simplify our analysis, and we're going to use a simple pendulum as a model for this physical pendulum. Now remember, when we are looking at simple harmonic motion, we need to look at all of the forces that are being exerted on the pendulum's bob in order to find which force is acting as the restoring force. So let's draw a force diagram on this bob. Here we have the force being exerted by the trapeze. Here we have the force of gravity. If we choose an XY coordinate system like this, we can look at the force of gravity in the y direction here and the force of gravity in the x direction. Keep in mind that the bob is always changing position, so these axes are going to be changing at each point in its motion. We'll just take a still shot and look at the forces at this point in time. So we can see from this diagram that this x component of the bob's weight is the net force acting on the bob in the direction of its motion. So it is what's pushing or pulling the bob towards its equilibrium position, and it is the restoring force right here. Now, when we remember our mass spring system, recall that the restoring force of that spring is not constant. Well, the same is true for a simple pendulum. The magnitude of that restoring force is at its maximum when the bob is at its maximum displacement. The magnitude of that restoring force is 0 here at equilibrium, and then it increases again until it reaches its maximum displacement over on this side of equilibrium. And the same is true for acceleration and velocity. They behave in the same way as with our mass spring system. Now, it's important to note that our simple pendulum, the motion in a simple pendulum is simple harmonic for small angle displacement. Small meaning less than 15 degrees. When the angle is less than 15 degrees, that restoring force is proportional to the displacement of the bob, and therefore pendulum motion is simple harmonic. Also, when we look at the mechanical energy in our pendulum system, we can see that the total mechanical energy is conserved and remains the same. However, the kinetic and potential change a lot. We can see the greatest potential energy up here and here and here. That would be when our pendulum is at maximum displacement from equilibrium. And we can see the kinetic energy is greatest when the pendulum swings down toward equilibrium and through equilibrium. That's when the kinetic energy is the greatest. And these are both fluctuating around so that the total mechanical energy always remains the same. Here's a table comparing simple harmonic motion of a pendulum and the simple harmonic motion of a mass spring system. You can see when these systems are at maximum displacement here for the pendulum, and here this mass is being pulled back from equilibrium. These things are true about force and acceleration and velocity. When both of these systems are passing through equilibrium, we have these truths holding, and then here, when the momentum of these systems is carrying the bob or the mass past equilibrium, so that it is then reaching its maximum displacement on the other side, these things are true. And back to equilibrium and back and forth, and we have our simple harmonic motion and the different conditions that are true for these different stages of the harmonic motion. Here's some advanced ideas. Look at spring shock absorbers, look at the conceptual challenge on page 437, or maybe you have some other ideas. I'd love to see what you come up with, and I look forward to seeing you in class.